Hello and welcome to our web seminar, A Beginner's Guide to the Digital Material Laboratory GeoDict. My name is Jürgen Becker and I am the head of Math2Market Support Team. In this online seminar today, I want to introduce the Digital Material Laboratory GeoDict to you. So when do you need a digital material lab? You work in an R&D department and you need to design materials, to analyze material properties, explore the behavior of materials, develop new materials, or optimize processes around your materials. Of course, as always, there are only limited resources: time, personnel, and money. And this is exactly the reason why you consider to digitalize your material development. You can run more tests and run multiple tests if we go to the cloud. So the agenda of today's seminar follows a typical workflow step by step. So at first, we will import an existing material into GeoDict, then analyze it geometrically. We will then predict the physical properties of this material. So we compute values here that we could compare with experimental measurements. Of course, we want to go further and create something new. But before, we want to create a digital twin of the real material. And this is then the starting point for the design of the new materials in the fifth step. And then last, I will give an outlook on some more advanced capabilities of GeoDict. And after the presentation and live demonstration, there will be some time for questions in a questions and answer session. So let's start. My name is Jürgen Becker, and I am the head of Math2Market Support Team. I was part of the founding team, so I've been with Math2Market since the start of the company. Before that, I was a research assistant at the Fraunhofer Institute of Applied Mathematics here in Kaiserslautern, which I joined after finishing my studies of mathematics. So now the term material can mean a lot of things, and I have to tell you what kind of materials we are talking about. So it's not the chemical structure, for example, new polymers that we are designing. What we mean with material is a porous material or composite material where the microstructure of the material determines the performance. So for example, open or closed cell metal foam, a metal wire mesh, a non-woven that may act as a filter or as a porous transport layer, a paper, a natural rock, maybe sandstone, can be carbon fiber reinforced plastic or other composite materials, and many more. So these materials, they play important roles in filters, batteries, electrolyzers, also diapers or any workpiece made of carbon fiber reinforced plastics. So how can you go from a real material lab to a digital material lab? So in the lab, you have to produce a prototype of the media first. And then you measure its properties to assess its usability for a certain function. Any material that you test has to be produced first, which is quite a lot of effort. And in a computer, you start with a digital model. And the model creates a computational mesh. In our case, it's a voxel mesh. And you can compute the properties of the material from there. And you can easily design new materials and even do an automatic parameter optimization. But there's some gap between those two methods that needs to be closed first. So, and to close this gap, we have to bring the existing material into the computer. And for this, we can use, for example, micro-CT or any other imaging technique. And this 3D image can then be segmented and filtered and turned into a computational mesh, and we can compute the properties. And in this way, we can bridge the gap between the real material and the virtual material by imaging the real material and bringing it into the computer. So these materials can be used in various application fields. For example, as filter media or membranes, as porous transport layers or catalyst layers in batteries, fuel cells, electrolyzers. Yeah, as composites, as materials used for thermal isolation. And you can, of course, also analyze processes in natural materials like rocks, where the pore connectivity is also important for example, fluid flow inside the soil or the rock. So the agenda of today's seminar follows a typical workflow step by step. So at first, we will import an existing material into GeoDict. We will then analyze it geometrically, for example, determine the pore or grain sizes. We will then predict the physical properties of this material. So we compute values here that we could compare with experimental measurements. And up to here, we're still working on the existing material. But of course, we want to go further and create something new. So we could directly jump here into creating new materials, but that's not advisable. Before, we want to create a digital twin of the real material. So that means that we want to create a structure model completely virtually. So we create it completely in the computer without imaging, but it looks like the real material. And this we call a digital twin. So it's a virtual reconstruction of the real thing. And this is then the starting point for the design of the new materials in the fifth step. And then last, I will give an outlook on some more enhanced capabilities of GeoDict. And after the presentation and live demonstration, there will be some time for questions in a questions and answers session. But you can also ask questions in the chat during the seminar. There are some colleagues of mine online, and they will be available to answer some questions while I'm talking. So let's start with the first section. So we will begin by digitalizing our existing material. Typically, you do not start from scratch when you want to design something new, a new material. So you already have some material that currently does the job. So you want to start your digital design with what you already have. And therefore, the first step is to bring the current material into the computer and to understand how it works. And when this is done, you start looking for improvements. And there are several options how to do this. The most straightforward is to make a CT or micro CT scan and then to import the 3D data. And I will show live now in the next minutes how you can import this in GeoDict. This only works for structures with features in the micrometer range. Smaller features cannot be resolved with this technology. So this is possible with FibSEM scans, and you can import them into GeoDict too. And for certain type of structures, it's also possible to generate 3D models from just 2D images. But this is a new app in GeoDict, and this will be the topic of another online seminar later this year. So now we switch to the live demonstration. So we see here on the screen the GeoDict user interface. And we will now import a micro CT image of a metal powder. So in the GeoDict interface, you find the import capabilities in the menu bar, and we choose the volume import to segment the 3D image. We then simply browse for the material and select the metal powder here. So here the geometry import dialog opens, and we could directly crop the image, but we don't want to do this. We want to simply import all the files and folders. What we have to select here is the voxel length, so the resolution of the image. And then we go on to the image processing dialog to have a look at the 3D data. So we see here 2D cross sections of the 3D data, and we can scroll through it in X, Y, and Z direction. Here. So we see here the slices in 2D in X, Y, Z direction. Here we see the histogram of the gray values. And here on the left, we have all the image processing tools available. So we can change the image size, we can modify alignment for the gray values. And also there's quite a number of image filters here. So we see here that there is some black and white, some random noise. And before we import and segment the image, we want to smooth the image to have less artifacts in the segmented image. So we select one of the filters, and as a demonstration, we take a simple median filter and can preview how this would work on this image. So we select then here a certain parameter range. For example, we want to check different radii for the median filter and see how this would affect the image. So we see here a small cutout of the original image, and then we see how a filter with different strengths would result. And then we can choose one. Well, maybe this is blurred too much, so we take a radius of 2 voxels, we select it, close the preview, and we can then apply the filter on the whole image. And see that it looks much smoother already. So once we filtered the image, the next step is to turn this gray value 3D image into a structure. That means we have to segment the structure into pore space and grain space. For this, there are also a number of tools available. The simplest is just a global thresholding. And we see here that if we choose a certain threshold, then everywhere where there's bright will become material, and where there's dark, it will become pore space. And you can see here with the slider how this would happen. And we can choose here on the left between different segmentation methods. So we here in this demo just take the simplest automatic Otsu threshold, because that already works quite well after we have filtered this image. So we can just create the segmentation and close the dialogues and have then the segmented structure here in the image. So we see already still the gray values here. We switch them off to see just the segmented structure, and we want to see the structure in 3D. So we switch to the 3D view, and we can choose some of the enhancements for the 3D view and see now here the grains of this metal powder. So what we also see here now, if we zoom in, how the computational grid in GeoDict is made. So we see that the whole domain is built of cubic voxels as to get them directly out of the micro-CT image. So there are no triangulations, no tetrahedrons, and there's no need to store complicated mesh geometries. And all the analysis and the computations that GeoDict does run directly on this voxel grid. So now we have digitalized the structure in the computer. But before analyzing it, we run one additional post-processing step. So, I mean, we have already filtered the gray values with a median filter, but we cannot be sure that all the noise was removed. So what we can do now is we run a component filter that removes small unconnected solid parts that may still exist here in the pores. And it's unreasonable that there exists such solid objects floating around in the air. So we will find them and then discard them. And there are a number of tools available in Process Geo. And there's this cleans structure tool that we can use to say, well, we want to check if there's any of these solid materials that consists of less than 100 voxels. So any solid components that is less than 100 voxels should be found. And we see that there are indeed some. And if we switch off the visibility of the red material, so we see that there's quite a number of these stray voxels here in the media that is just flying around in the pore space. And well, this is obviously some noise that is left over, so we remove them from the material. For this, we reassign the material here, the green, make to the pore. And if we reassign this, we see that this green material disappears. So now we have removed the noise completely, and we can simply save the structure for later use. And I select project folder here for today's seminar and store the structure now as metal powder GDT. So this was the first step. What do we have achieved by now? We have digitalized the real material and now have a 3D structure model of it in the software. And the next step is now to analyze this structure geometrically. So, we had the gray value image, we have made a structure out of it. And then now for this sample of powder, GeoDict GrainFind module will be possible to separate the particles and analyze the particle size distribution. So we get some size distribution of the particles, and you can compute, of course, pore sizes, grain sizes, calculation points. And I will now show how to do this. So again, we switch back to the live demonstration. And now want to find out what are the grain sizes and how can we identify individual grains in this material. And for this object identification, there's a module called GrainFind, and this allows to identify single grains in the. So, and in fact, you can leave everything, all the parameters on default, except that I want to show one additional result. I have to switch on an extra option here before I run this. So what is happening here? After the segmentation, we have a black and white, or rather here a red and black image. The software has understood what is pore space and what is solid material. But that's all it knows. While the human eye or brain, and we can directly identify the shapes in it. But the software has some difficulties with it, and it does not understand initially if something is a fiber or grain, or if it's an ellipsoid or sphere. And this is what GrainFind is now doing. GrainFind tries to understand the structure and to identify the single objects in it. And once we have done this, we can make the statistics on the type of structures. So now it should be ready. Yeah, so here we are. And at first, in the results, we will have a look at the identified grains. So we can load here an index image where every grain gets a different color. we load that. We want to set the structure to be invisible so that we can see just the index image of the identified grains. And so here we see in a different color for every grain, and we see that we have only identified grains that lie completely inside of the domain, because of course, if the grain is somehow cut by the domain boundaries, we cannot measure the grain size because there's only a part of the grain in the domain, and we don't have the full information about the size of it. So everything what's cut by the domain boundary has been removed, and only the grains that are completely inside of the domain go into the analysis. And this analysis is then available. So, for example, if we want to have the number of the grain diameters, we can have a look at these plots here and see the distribution of volume equivalent spheres. So this would be the diameter of volume equivalent spheres, where every sphere fits one of these grains. So, but we can also have a look at this size distribution directly in the image. So we can load this grain size distribution too, and have the grains colored with their image size. So we want to see this only on the solid material. So we switched it off, and we see here that all the grains on the outer part, they haven't been analyzed, they're still in blue. So, but if we move the slider here, we see all the grains that have a certain size with it. The red ones are the big ones, and the blue ones are the small ones. And if we move the slider here, we see only here the biggest of the grains remain. And they go one by one. That's how we can find the geometric properties. But not only geometric properties are measurable with GeoDict. The true power of the digital material laboratory is that you can also predict the physical properties. So, and what are those? Well, we have here in the menu, there's this predict, and there's a number of modules that allow to compute certain physical properties. And of course, for different application, for different materials, very different physical properties are interesting. For some, you're interested in acoustic properties. Some materials, you want to know advective or diffusive transport. If the material is a battery electrode, you want to compute how you can charge this electrode. If it's a thermal isolator, you want to compute how thermal conduction works in this. Other materials, in a gas diffusion layer, you're interested in the diffusion properties, mechanical stiffness, for filters, the filtration, and last but not least, of course, also the flow properties for single-phase flow, but also for two-phase flow, which is very interesting if you consider natural rocks or soils. You want to analyze how water, oil, or something else flows through it. We will now have a look how to compute one of these physical properties, and we will load another example for this. So instead of the metal powder, we will have a look at the fibrous material and load this now. So switch again to see just the structure and have to remove all these results of the previous computations. So we just have the structure here in memory right now. So this is an air filter, and I want now to demonstrate how to compute the flow through it. Flow happens in the Z direction. So here from top to bottom through this material. And to compute the flow, we can use FlowDict, and we select the Stokes equation for slow laminar flows. We open the dialog, and we have to choose the fluid that flows through the pores, of course. Take simply air, and well, that's it for what we have to choose as materials. We then have to choose the boundary conditions of the simulation, so in which direction should the flow happen, here in Z direction, and what's, for example, the mean velocity that we set. So we prescribe the mean velocity and want to compute the pressure drop in this case. There is a number of additional solver optimization parameters, and we leave them all on the default values for now, and simply click Run to start the computation. So, and now you experience live the speed of the solver that we're using here. So, I mean, it's not the biggest example, but it's still 375 times 375 times 150 grid cells, which makes up a little bit more than 20 million voxels. And there are 4 unknowns per voxel. We have the velocity vector, these are 3, and the pressure. So this is a partial differential equation that has more than 80 million unknowns. So it's not so small. But due to the simple voxel grid that we're using, this computation needs only 3 gigabytes of RAM. So it fits easily on a laptop. Yeah. And actually, we're running the computation here on my laptop. And this is just an Intel i7 processor with 2.7 gigahertz. So nothing fancy. And we see we have already the result here in about a minute. So what have we computed? As I said, we have prescribed the flow velocity and have then computed the pressure drop over the medium as a result. And we can have a look at the flow field that we computed and load this into the visualization. And okay, we see here color-coded the flow velocity, but it's nicer if we don't look at this color coding, but at the streamlines, or even nicer if we switch visualization to tubes. And yeah, we see here how the flow goes through the material, and we can clip a little bit through it to see more of the flow paths. So we have seen that we can analyze the existing materials geometrically, and also we can predict some physical properties like the permeability for fluid flow. But so far, that means that the material must be produced first, because we have operated on a micro-CT scan of something real. So, but in the end, we want to be inventive and create something new even before it is produced. And so now we go a step further and create structures completely in the computer, so without image import. And the first step here is now we want to create a digital twin of the real material. I mentioned the term digital twin many times today, but what does it actually mean? Especially in regards to these complex microstructures. So in general, if people talk about a digital twin, they mean a digital model of some real physical object, like kind of a car, and this should be a 1-to-1 match of the object. So for the microstructures, we cannot aim to create models that have the fibers or the grains exactly at the places as the real material. And in fact, this is not necessary. So Instead, we have statistical digital twins. And that means that we have a set of parameters that allows us to generate a microstructure that has the same physical and geometrical properties as the real material. But that doesn't mean that the fibers are exactly at the same position as in such a nonwoven. It's not possible, but it means that the generated digital twin has, for example, the same pore size distribution and the same permeability as the real material. The steps that we have to do to get a statistical digital twin is, well, we start with the real material, we make a 3D image of it, we segment this 3D image, so then we have the real material into the computer. We can analyze this image, and then we rebuild it virtually. So it means we don't use just the import, we create an image that has the same statistical properties, but we create this completely in the computer. So, but how do we rebuild these structures? So the structure creation of such materials is a stochastic process. Based on a set of input parameter, we kind of throw a die, and then we place a fiber somewhere in a random position. And then we place more and more fibers in random positions until we reach a desired grammage or porosity. So as input, we do not prescribe we have a fiber at exactly this position and one at exactly that position. We describe what the fiber cross-section or shape is, and then we have kind of probability distributions for the diameter, for the orientation or the location of the fibers, and these fibers are placed randomly. So coming back to this metal powder example that we have analyzed first with GrainFind, we had this example, we analyzed it, we got the grain size distribution, and we can now use this information as input for the structure generation. And if we take the results from GrainFind into GeoDict StrainGeo, then we can use this statistical approach and get randomly put in grains that have the same size distribution than the original structure. And then we put on grains, and more grains until we have the same amount of grains as in the original structure. And then there's one additional step here, because if you just place them randomly, you see here they are kind of overlap. And that's, of course, not what happens in the real material, where the grains are separate. So there's one step also in the construction process that these grains are shifted so that there is no overlap remaining. And when we do that, we see here the original structure, and then we see here a digital twin created with GeoDict that has the same grain size distribution. And yeah, it looks very similar, except we see here in the original, we have more surface roughness, because these are perfect spheres or ellipsoids sometimes added. Yeah, but there are actually also tools in GeoDict that allow to add surface roughness. So one could improve this even more, add some surface roughness, and then be closer to the real material if it's necessary. So back to the live demonstration. I want to demonstrate now how to create a digital twin on this fiber structure. So remove this flow result and get back the clipping here. So we have this fiber structure and we want to create a digital twin of this structure. So we don't have grains here. So how do we analyze it? Well, there's another tool. It's called FiberFind instead of GrainFind, and this can be used to identify the fibers in it. So I open the parameters here, and for the fiber identification, we will use a neural network. So this neural network was trained by us and is included in GeoDict, and it can be used to identify fibers in a certain diameter range. And that the current fibers here fit into that range. So we use that, and there's one value I have to set here as threshold. One has to take a lower value here. That means if fibers are cut into multiple segments, and one has to raise this value. If fibers are identified as 1, that should be 2. So I have checked this before, and 0.1, that it's a good value for this example. So we click OK here, and then we click Run. So again, what does this algorithm do? It needs to turn this, again, still black and white data into individual fibers. And this is done with an AI that we trained with GeoDict generated data. So that means we have used FiberGeo to create hundreds of non-woven media models with different diameters, porosities, or fiber orientations, and so on. So we have created a lot of 3D structures with a known solution. And then we trained the AI to find the individual fibers in these meshes. And this AI can now also find the fibers in segmented 3D images. And why is this useful? Well, once we have identified single fibers, then again we can analyze these fibers for the diameter, for the orientation distribution, for the curvature, and so on. And these are exactly the values, of course, that we then need to rebuild the structure virtually. One last progress bar, I think. Here we have the solution. So we found almost 300 individual fibers in the structure. And as with the grain find, we can have a look at the identified fibers, where again we load the index image to see the color-coded individual fibers. So every fiber has a different color. And we see that there are some artifacts there where the fibers are not completely inside of the domain. Then it's difficult to identify an individual fiber if the fiber is not completely in the image, that's clear. But otherwise, we have found the fibers rather well. So, but the FiberFind has not only identified these individual fibers, but also determined the analytic fiber objects that match these fibers best. So we can load here the curved fiber fit tool, and then see here in red now the matched fibers, so the fibers that were matched to the original fibers that are still here. We still see here the color coding. And these are now fibers that are not just a collection of voxels, but we have set of parameters, position, diameter, direction, segments, and maybe the diameter changes over the segments. And we can now compute all the statistics again from these fibers here. And if you look at the result viewer, for example, in the plots here, we see we have a fiber diameter distribution. So fibers are somewhere distributed around 34 microns, and the smallest pieces are below 25, but these are maybe also the cut fibers that are at the boundary of the domain. Now, we have analyzed the fiber structure, and have in the report here a lot of parameters. And with these parameters, we can actually start to rebuild this structure. And for this, we go to our structure generation tool, FiberG. So we open the dialog, and now instead of entering all the parameters, I will have before the training filled this dialog with data, and I will now load the data, and we'll just have a look at the values, because this is quite a number of parameters. So first, domain size. We want to create exactly the same domain size as the original structure, so we enter that here. And then we want to have the same solid volume percentage as the original structure. That was 24%, so we enter that here too. So then on the fiber options, we have to set the fiber diameter. So these values are the ones that had been reported by FiberFind. So they have the mean value around the 34 microns and some standard deviation around it. We have to prescribe a fiber length. So this is a parameter we cannot find out with FiberFind, because the fibers all were longer than the domain size. So we just take a value here that's also longer than the domain size. We simply want the fibers in the model to go from one side to the other of the model, because they're in reality they're some millimeters long, and we only have a cutout of a few microns. So then we have uniform distribution of the fibers in the domain, and we have to set the fiber orientation. And here we have to can prescribe an orientation tensor, but these are simply the values that FiberFind has computed from the original parameter. So we have a certain, the fibers mostly lie in the XY plane, only we see in the Z direction, they're not oriented in the through plane direction, and we have a little bit more fibers are oriented in the X direction than in the Y direction. So there's some, most likely some machine and cross machine direction to that is in the fibers. So, and if we click OK, then we can generate a structure. And see here a structure that is already very close to the original structure. There's one difference to the original structure. Now in this quick generation method, we still allow the fibers to overlap, so they can go through each other, which is of course not possible in a real non-woven. And in GeoDict we can also avoid that, but it takes somewhat longer to compute. So it takes a little more than 6 minutes instead of just these 4 seconds. But then we get a 3D structure without overlapping fibers as well. And I have computed that before, and will simply load the structure where the overlap is removed. And then we have fibers that don't intersect with each other in the structure. Here's the comparison now between the original structure and the created digital twin in this way. So, but why it's so important to have such a digital twin structure? Well, we can make the geometrical analysis and predict the physical properties also for the original structure. But what we cannot do, the original structure alone, is the virtual material design. So if we have a parameter space with lots of possibilities for a structure, we have to start somewhere. And then it's good if we know what the digital twin of the current material is. So we know where in this parameter space our current structure or real structure is located, and then we can go there from there in any direction. And this is why you need the digital twin. You need to know where you start, because without you can make a lot of models, but it's difficult to relate them to the real material. So, but once you have your starting point, then it's easy to modify the structure with GeoDict. And you can compute and change very different things. For example, for the fibers, if you have the original, you can select smaller fiber diameters, or can make a thinner fiber media. You can add binder, can make higher porosity. You could make media with different layers, or you can add a second fiber type. And of course, the advantage of doing these modifications digitally first is that you can create them with almost no cost in the computer. And it would be very expensive to produce all these kind of things in the lab. And in the computer, you can try out what would work, and only if it works and the parameters look like that this will be a good material, then you try to produce it. Yeah, and with this slide, we have reached almost the end of the presentation. So I will just give now a short outlook of what else more complicated things you can do with these material models that you have created in GeoDict. So give some glimpse of what can be computed. So, and the first example is about filtration. And we see on the right side here the filter media, where for the better visualization of the depth filtration, fibers are not visualized in this part, so only the particles. And let's start it again here. And as the filtration starts, more and more particles get deposited here in the filter, and the filter clocks. The pressure drop will rise. And here on the left, we see plotted where in the media the dust is deposited. And then we see at the end, it's just there in the on top of the media, and there's a dense filter cake there. And well, in real life, once that happens, the filter is clogged, the pressure drop goes up very steep, and yeah, filter has a lot of energy consumption, and you have to exchange the filter, and that's what you want to compute when this will happen. So, and the next example is yeah, porous transport layer. So you see here a porous transport layer that is used in an electrolyzer, and typically they are compressed by a backing layer that consists of some flow channels for air or hydrogen. So we have a channel rip patterns that causes an inhomogeneous compression of the media. And if I run this computation here, you see the deformation and the resulting mechanical stresses. You see they're higher here below the rip than under the channel, and you see how it deforms. And you can see here in the chart that there's actually a non-linear increase in the stresses because you get additional fiber contacts during compression, and it becomes harder and harder to compress the media further. So the next example is a model of a battery with a graphite anode and a lithium nickel manganese cobalt cathode. And here we have a separator in black, and we have some current collectors on both sides of the cathode and anode. And if we start this, we will see here color-coded the ion concentration during the charging of the battery, where we charge from 20% to 70% state of charge. Let this run again because it goes rather quickly. And you see that blue and green, this means low and high concentration, and this switches the sides in the course of the simulation. So, and it's the last example is from digital rock physics, and we see here the scan of a cylindrical rock sample. So it's a Gildehauser sandstone, sandstone of a certain area. And the animation will show the primary drainage. And here in this case, drainage means that oil replaces water. And this corresponds here to the red capillary pressure curve. So, and yeah, with GeoDict, then you can compute drainage, and then afterwards imbibition and the entire hysteresis cycle in this sandstone. So if oil replaces water, then water replaces oil, and back and forth. And this is, of course, interesting for companies that try to get the oil out of the rock. So yeah, this was the last slide of my presentation, and now I'm open for questions from the audience.
There's one question here about the battery simulation. Can we import electrode material simulated from elsewhere?
Yeah, so I mean, you can import materials. Yeah, if you have them in any black and white voxel format, but also if you have them as cut data, you can import them in GeoDict and then run computations on that in GeoDict.
And a similar question also about, so basically this tool allows us to model from scanned media.
Yeah, you can model from scanned media. I mean, you can also model without a scan. Then it's a little bit more complicated maybe to find if you want to mimic your real material to get the right parameters. If you just take them from what you know about the media or what you can see from 2D images, you have to think a little bit more about what the right parameters are that describe the material. But of course, it's possible to. You can directly start with FiberGeo and GrainGeo, enter some parameters and get a material model out of it.
So there's one question more about, did you use the AI tool to regenerate the grain pore structure?
Yeah, so I didn't show that here. I just had the results on the slide. But you can directly in GrainGeo, there's even an import button where in the GrainGeo dialog you can read the results of GrainFind, and I did just this. I just imported it and clicked run, and then this was the output that I showed on the slide. The only issue is that because of there's a 60% solid volume fraction or something like that, and the grains are not allowed to overlap, it takes about 10 minutes or so until all the grains are at the position that they don't overlap. So it's not suitable to demonstrate this live. That's why it was on the slides. But it's even easier than for the fibers because you can just import the result.
Okay, and there is a comment about, hello, thank you for the presentation. Is it possible to generate yarn geometries by only specifying the warp or waft geometries, number of plies, etc.?
Yeah, I mean, we have weave geo, and there it's possible to have different woven materials in various weave patterns. And yarn, one has to look at the specifics, maybe, what's possible and what's not, but in general, yeah.
And there is a question about if I can make digital twin of anisotropic materials such as polymer composites with continuous fibers.
Yeah. Yeah, I mean, the fibers is always anisotropic. I mean, almost always. have a certain preferred direction for the fibers. Like we had already here in this air filter media, you have clear orientation in plane, through plane, and there was even a preference of the X direction over the Y direction. So that's directly included. I mean, that's this orientation tensor that prescribes this. And yeah, this works as well for composite materials. Most often it's even easier for the composites. They're often more aligned than, in my experience, than this non-wovens.
There's one question here. Can the program find the magnetic, electric, other materials properties?
Electric, yes. Magnetic, I don't think that's it. No, magnetic is not included. Yeah. But yeah, electric conductivity or ionic conductivity you can compute. Yeah.
Then there is one last question here. Thank you for the presentation. I would like to ask, how can I get the program?
Yeah, if you're interested in evaluation, just write us an email.
So there's on our website also a place to type your details to request an evaluation license.
Yes,
and
yes.
you're welcome to do that, and you're welcome to email us, any of you with more detailed questions. We're happy to help. Thank you, Jürgen.
Last remark, there's the next seminar again in March, in just 3 weeks. It will be given by Tabea, and the topic will be adsorption processes in porous media. Yeah, 3 weeks. I think it's also Tuesday afternoon at 4 p.m. The registration is, I think, not open today, but it will be open this week, I'm sure. So you can register by the end of the week if you're interested. And yeah, with that, I would like to thank all the participants for your attention. If you have questions, you can write an email to support or ask questions in the forum. When you have to apply for an account there, or you can also find many answers directly in the user guide. With this, I want to close the seminar. Thank you again. Have a nice evening. Goodbye.
Goodbye.